Chapter 8, Intentional Electromagnetic Interference, or IEMI. So far we have been dealing with EMC issues where the source occurs naturally, either due to natural phenomena or due to the inherent nature of the equipments that we use, interference created by equipments or by lightning. But it is also possible to intentionally create electromagnetic fields with the sole purpose of disturbing sensitive systems. This can be done by rogue elements in the society or even enemy countries. So this chapter will deal with some of the special issues related to that type of a scenario. The outline. So first, in module 8.1, we will look at what is meant by IEMI, what are the main characteristics, and how intentional EMI is different from the normal electromagnetic interference issues, and why it is such a concern now. Then after that, in module 8.2, we will take the critical infrastructure. Critical infrastructure means, in society, power lines, communication lines, economic infrastructure. So everything that is required for the smooth functioning of the society. Because often for the rogue elements, this type of critical infrastructure is an attractive target. So we will look into what are the special issues related with that, and talk about the mitigation philosophy applied to IEMI. First of all, what is meant by intentional electromagnetic interference? It is often defined by this following quote: intentional malicious generation of electromagnetic energy, introducing noise or signals into electrical and electronic systems, thus disrupting, confusing or damaging the systems for terrorist or criminal purposes. So here there are several elements to it. First of all, in IEMI there is a component of intention. It is something not that just happens, it is intentionally created. So that itself introduces several challenges. We will see that. Then this whole purpose is not any useful purpose. It is for disrupting, confusing or damaging these systems. So it is not just accidental. Then the idea is to create chaos into that particular system or particular establishment. Now, unintentional EMI, that is usually taken care of legislation and standards. And we have seen EMC testing and standards in the previous chapter, and we have seen the different principles that are used in protecting the systems. So unintentional EMI are usually taken care of by this type of measures. And say for example, if any product is marketed in European Union, there are European directives requires the CE marking that you can see in the products. And other international and national standards on EMC are also available in all countries. Then when it comes to aircraft, you have much more stringent condition for EMC because of the catastrophic consequences of EMI into aircraft. So there are special directives for civil aircraft issued by civilian aviation authorities, including protection against lightning, one of the severe electromagnetic disturbance that you can find in the aviation circles. So all this will take care of unintentional EMI. Now when it comes to intentional EMI, it is still developing the regulations and other things, and often it is so difficult to make regulations because often it is the intent that creates these problems. So in civil scenarios, it is often denoted as electromagnetic terrorism because it is for terrorizing the civil society that sometimes this type of issues comes. And the levels of EMI are usually much higher. The threat levels are much higher than unintentional EMI because there is an intention behind it. So it is much more complicated to take care of intentional EMI situations using the normal civilian standards. So that is the focus of these modules. Now, why the reasons for society's increased vulnerability to IEMI? So why society is increasingly vulnerable to IEMI? So there are different reasons for that. So we can look at these reasons from, let's say, from the victim side or looking from the source side. So from the victim side, we can see that society is extremely dependent on interconnected electrical and electronic system for its function. This was not like that several decades ago. Now, imagine in advanced societies, if there is a power outage due to certain incident, widespread power outage, then when power is gone, communication systems will die down soon because battery backup will be gone. Then water distribution system, transportation system, all of them are dependent upon power and communication, or financial transaction systems. So you can imagine a scenario in which there is no power in the society for several hours, and all these systems can be disturbed. And since modern society, especially in the Western societies, these systems are so well functioning that you don't often have backup. Normal homes or normal business establishment don't have backup power generators because power outage is such a rare phenomena. Then increased use of sophisticated and sensitive commercial off-the-shelf electronic for critical equipments. Now, several decades ago, often in critical equipments, there are specially made components being used, made for that, and one can harden these systems as one wish. But due to the pressure to reduce cost and other reasons, often now commercial off-the-shelf equipments are used even for critical systems because you need so many systems, and it is often easier to buy those things rather than make specifically for those applications. So these systems are tested against normal EMC in its normal environment. So they are not really meant for withstanding intentionally created EMI. Then miniaturization of components make it that even lower level of signals are used in the system, and you don't require that high levels of disturbance to penetrate into a system for destroying it. Then legal EMC requirements for civil products are in general insufficient for protection against IEMI because you don't expect such high levels of source. Maybe civil aircraft is the only major exception to the rule because there you specify at such a high level of EMI, you expect such high levels of electromagnetic interference that civil aircraft can withstand usually IEMI scenario. Now, on the source side, this is kind of a dual system. When the society is becoming more and more dependent on interconnected electrical and communication systems for its smooth function, terrorists and other criminal elements are more attracted towards targeting those type of systems. So there is a motivation for them to do that, and often they can do this type of attack anonymously, because you don't leave any trace behind, unlike other type of sabotage. Electromagnetic sabotage doesn't leave that much trace behind because it's just a transient event. And more components are available that can be assembled to homemade sources. Even a microwave that you use in homes has a powerful source, a powerful microwave source, which coupled with antennas can be made as a crude electromagnetic weapon. And there is a lot of information in the internet, and expertise is widely available nowadays. And even commercial high-power EM sources can be just bought off the market, like used radars and other type of equipments are freely available, which can be converted into weapons. Coupled with this availability of sources and the anonymity that IEMI attack often provides, becomes more attractive for the criminals to use those type of methods. Now, a biggest concern regarding intentional EMI is critical infrastructure for various reasons. If you have a small device with a well-defined boundary that can be measured in sub-meters, like a cube or something, you can encase it in steel armor or shielding and such protection components. All kinds of EMC mitigation methods we have used. Just increase the specifications and you can have fairly good protection against IEMI also. But that's not possible with distributed infrastructure. Say, for example, if you take Sweden, this is a map of Sweden, many of the critical infrastructure, it spans the whole country. That is more than thousands of kilometers. And they are all interconnected. Radio, television network, traffic control system, food and water supply, telecom, power, financial system, computer networks. So if power and telecom is targeted, often the rest of these things also will die down. So they are all interconnected. And the sources can be wielded by criminals, competitors. If it is kind of industrial complexes, disgruntled employees. There were cases like that when disgruntled employees were trying to sabotage their own factories or business establishment, protesters. Then even military adversaries, because IEMI does not leave much trace behind, and then even without declaring a war, one can target other countries' infrastructure. So these are the issues. Now we have seen this classical picture from before, the basic decomposition of an EMC problem. So you can have a source and you can have a victim, and there's a coupling path in between source and victim. So 2 is the coupling path, 3, 4, 5 are the victim, where you have this front door kind of coupling, then internal coupling and the system response, etc. Say, for example, a source has to be defined, for example, frequency envelope, power, polarization, angle of incident, etc. And one of the basic tenets of EMC EMI mitigation strategy for achieving EMC is that we know something about the source that is going to happen in that equipment's normal environment of use. So we have some idea about frequency envelope, power, polarization, angle of incidence, source characteristic, etc. So this is a basic assumption. With IEMI, we don't know, we can't be sure, because it can be any source. Then coupling paths of electromagnetic energy, whether it is near or far field coupling, properties of the medium, whether it is conducted coupling through cables, etc. We have some knowledge. And receiver boundary, what are the apertures, filters of the equipment, etc. Internal coupling of the receiver, whether things are radiated, what are the absorbing materials there, ground planes, this knowledge we have, and response of the component, how the system will respond. So this is, we try to understand all these 5 elements in a normal EMC scenario. Even in IEMI, this is the same strategy that we will be using. So there is no difference in the approach. The only thing is that we need to have some extra thinking to be put into those. So this we will see with an example later in the module 2. Now, comparing IEMI to normal EMI, issues when aiming for EMC in an IEMI scenario. So let us look into that and try to see what are the difference between normal EMI and IEMI situation, industrial EMI situation. First of all, regarding the source, in normal EMI, we assume that we know something about the source in that particular environment. But however, in the IEMI scenario, it is very hard to estimate the source characteristic, because we don't know what kind of source the perpetrators will be having. So unconventional industrial sources are continuously modified. So you need to have a continuous evaluation of the threat perception based on freely available technologies in the society. Then in normal EMI, we have a fair idea of the coupling path. Say, for example, if you have a building and if there is a lightning happening to the building, we know that, okay, it is the air termination where the lightning will be attaching to. But of course, you can have lightning type of pulses that can be generated in equipment. At least small lightning can be generated by small equipment, and if these type of things are directly injected into a cable coming into the building or a power socket outside, then of course the building is not designed for that type of source appearing in that type of places. So you can have many unconventional coupling paths because of that. So unexpected ports for injection of disturbances. So this is a big challenge in the IEMI scenario. And therefore the physical and electromagnetic topological boundaries do not coincide. Say, for example, perpetrators can come into a building with powerful sources. Unless there is a possibility that these type of sources can never into that area. Suppose if electromagnetic topologically we have defined zone number 1 like that, and defined what are the sources inside zone number 1, and if we don't have a physical boundary for that, then perpetrators can bring in sources more powerful into that particular zone. So this is what is meant by that physical and EM topological boundaries do not coincide, because you don't expect a a lightning type of pulse directly striking inside a building, whereas in the IEMI scenario it is possible to do that. I'm just giving an example. It can be some other source, not necessarily lightning. Then the philosophy of using codes, commercial off the shelf, so that equipments are tested for specific environments where normally it is meant to be used, and it may have very little in common with the eventual IEMI environment, because the normal codes equipment, when used in a place where it is not an attractive target for perpetrators, then of course it will function in that environment. But when it is used in an environment where someone is targeting with an IEMI source, then it will not function. So the challenge of intentional EMI, we have seen that the main difference between EMI and IEMI is the intent. And because of this intent, it is very hard to predict what your source will be in a given situation. So this picture you have seen, what are the possible spectra, the possible EMI spectra. Now we have to say that the whole spectra can have the potential to be used for IEMI attacks. So it can be even injecting a DC current into a ground, a telecommunication ground, to create disturbance. So here in the spectra, you have this lightning spectra, you have normal EMI environment spectra, 10 kilohertz, 1 megahertz, up to few megahertz you can have. Then you have HEMP, nuclear EMP, the high altitude electromagnetic pulse, that can go up to few hundred megahertz. Then you have now other type of sources used in military and other scenarios. For example, you have narrow band high power microwaves and high intensity radiation fields. So they are basically short bursts of sinusoidal pulses at few gigahertz, if you take the frequencies. So it will be very narrow band, like very targeted kind of band. So military systems use this. There are HPM weapons used by military in destroying enemy systems and all. So these are narrow band system. Then there is another type of pulse, ultra wideband. So the more definition you will see in the next page. So ultra wideband is also a big concern. So as the name suggests, it is a impulse wave, not sinusoidal, but just an impulse. And impulses have got very wide frequency band. So frequency band can be of the order of hundreds of megahertz for this. And they may not be of extremely high power compared to HPM. It may be of less power, but then attractiveness of this as a IEMI source is that it can excite several frequency bands in the equipment, where it can introduce some resonances and all. So with HPM and all, it is just one narrow band, and if you strengthen those narrow band, protection against those narrow bands, then of course your equipment is saved. But with the ultra wide band, it exposes the system to extremely wide frequency range, and unfortunately there can be some frequencies where the system may go into resonances, or it may be susceptible. So this is one difference between EMI and IEMI, the intent. So the Volt's frequency spectrum is open for IEMI. Then compromise of zoning concepts. Zoning principles may be compromised. We have seen in chapter 5 what is the electromagnetic zoning principles. like say this is zone 0 where EMP and lightning and all kinds of things may happen, then inside you expect that these shields and other interference diverters will reduce the intensity of the sources to certain level. So you have some idea of what these levels should be. Then again, to sensitive circuits you have another zone 2, 0, 1 and 2. So there it will be even less. But this is workable with naturally occurring EMI and normal equipment EMI. But if suppose this is a big industrial complex and someone is entering with a source hidden, then immediately you are breaking this electromagnetic topology called zone boundary, because there is nothing preventing that person from entering with the source inside. So one can come to the most sensitive part of the facility, and you have a source that is totally unexpected. So compromise of zoning concepts is possible in the IEMI scenario. Topological and physical boundaries do not coincide. You can have unusual port of entry that normally you don't expect, and unexpected source characteristics. So all these things are possible. Then this is especially a big challenge for large distributed systems like railways, because if it is an industrial complex or an equipment, you can have these zone boundaries like this. I mean, to some extent, equipments it is possible, you can protect well against. Even with a physically limited industrial complex, you can try to have some sort of, say like a nuclear reactor complex, you can have some kind of a control. But completely distributed system like railways, power systems, communication system, etc., it is more difficult. Now we see some example, unexpected port of entry. This is an example of a control center, automatic control center for railways. Keeping trackside equipments. You have an antenna on top of this mast for communications, etc., and cables going into the building. So nicely constructed building with the shield cladding inside, no windows. There's a perimeter fence, so access is very difficult, etc. But at the same time, perimeter fence is mainly for keeping out animals and people straying into it, out of curiosity, not meant for someone determined to get into the things. Say, for example, you can easily scroll into using this through these gaps, etc. Then once you come to the building, you have equipments outside, power sockets outside, power socket outside, and the building is on top of pillars like this, so you have all kinds of cables coming inside. So it's very easy to access the cables and power sockets outside. But in the normal EMC scenario, you don't have to worry about it, because you don't expect any. These are just for convenience, this power socket outside for cutting the grass and other maintenance things. But if someone is injecting a high impulse into this, then it goes into the sensitive system inside, distributed into inside, or through the cables it can be, impulses can be brought inside. So this shows the unexpected port of entry in the case of IEMI scenario. Now there have been experiments conducted, that experiments are reported in these publications, to see the ability of differential mode, ultra wideband transients, to penetrate deep into a facility. Ultra wideband have extremely large frequencies, and so often it is thought that it will be dissipating very fast. but not necessarily if it is in a differential mode. Differential mode is more like a transverse electromagnetic mode with very low loss. So it can really travel a long way compared to common mode, where most of the energy is radiated out and dissipated. So this is from a generator, differential mode signals that is injected in a building outside in a power socket between phase and neutral, or between one of these conductors and the earth wire. Then you see how it is propagating inside. After 1 meter of propagation, you can you have this particular level of voltage, and after 2 meters of propagation, this voltage, it is attenuating but not fast enough, so you can penetrate deep into the facility with the differential mode ultra wideband. So what is meant by ultra wideband signal? That can be quite attractive for perpetrators for IEMI purposes. So these are transient signals. So this is an example taken from this thesis. That can have rise time, sub-nanosecond rise times, or even nanosecond rise times, and fall times of the order of nanoseconds. So here it is time. So this is 10 nanoseconds, 5 nanoseconds. So within few nanoseconds the pulse is over. So this has got extremely wide band. So you can see that this is of the order of 10 megahertz here, 100 megahertz here. So you can have, if you take, you can have several hundreds of megahertz in bandwidth. So sub-nanoseconds or nanoseconds rise times and nanoseconds fall times, and usually large bandwidths of the order of 100 megahertz. So due to this large bandwidth, it can excite several vulnerable frequencies within the victim. Now, HPM are more narrow band. We have discussed that before. High power microwaves, short burst of sinusoidal waveforms separated in time. So they are quite narrow band. Now, HPM has been, you can have extremely powerful sources with HPM. So HPM sources have this ability to do physical damage on common systems, unprotected equipment, say for example cars, personal computers, etc., has been done in this publication. So this table is taken from there. So they have seen that if you have an HPM van, so a 10 megawatt source, because they are quite huge, 10 joule energy capacity. So then, you don't come close to a critical system, but suppose you are 50 meters away, then it can create permanent physical damage. And 50 meters, it can do upset and damage. And 500 meter also it can create upset and damage. So this may be, one can recover from it, or one can after some time, but when the source is on, the system is not available. Now, HPM suitcase. So in a suitcase, it can penetrate much deeper into the facility. So to the close vicinity, it can come. So the source is at least 1,000 times less in power, but still, 100 times less, but still, you can have permanent physical damage in close vicinity, and it is a threat up to several tens of meters. Then similar kind of effects can happen with ultra wideband or high power microwaves systems. but permanent damage likely requires very high pulse repetition frequency. So there were several tests done like this on equipments to see what could be the possibilities, and it is known that it is possible to disturb systems by sources that can be carried in small briefcases, suitcases. 8.1.